Tonight, we're embarking on a gentle journey through one of the universe's most haunting melodies, echoes from the very beginning of time itself. We're going to listen, quite literally, to the first sound the universe ever made. I'd love to know where in the world you're drifting along with me tonight, and what time it is in your quiet corner of existence. There's something beautifully fitting about exploring the cosmos at different hours, each of us scattered across time zones, yet united by the same ancient starlight that's been traveling toward us since before Earth had oceans. If you find tonight's cosmic lullaby soothing, or if it stirs something wonderfully curious in your sleepy mind, I'd be ever so grateful if you gave this video a gentle like, perhaps subscribed, or simply let me know in the comments where you're listening from. It helps other wandering souls find their way to these peaceful explorations of the universe. Now, I do hope this isn't so fascinating that it keeps you awake. But if it does, well, at least you'll drift off knowing you've heard the universe's very first song. So settle in, let your breathing slow, and prepare to listen to something that's been humming through space for nearly 14 billion years. The story begins, as all the best stories do, with a moment of perfect silence. Not the comfortable quiet of a library or the hush of falling snow, but the absolute, complete absence of everything. No space to hold sound, no time for it to travel through, no matter to vibrate and create those waves we call music. Just nothing, waiting to become everything. And then, in an instant so brief it defies imagination, everything changed. The Big Bang wasn't actually a bang at all, despite its rather dramatic name. There was no explosion echoing through empty space, no cosmic fireworks lighting up a dark sky. Instead, it was the birth of space itself, the first breath of time. The moment when the universe began to hum its opening note. In those earliest moments, the universe was unimaginably dense and hot, a seething ocean of energy and particles. Protons and electrons danced together in a cosmic ballet, but they couldn't quite settle down into the stable atoms we know today. The universe was opaque, like trying to peer through the thickest fog imaginable. Light couldn't travel freely. Sound couldn't propagate in the way we understand it. And yet something extraordinary was happening. The universe was singing. You see, in this primordial soup of matter and energy, pressure waves were rippling through the cosmic medium. These weren't sounds as we know them. There were no ears to hear them, no air to carry them, but they were acoustic waves nonetheless. The universe had become a vast musical instrument, vibrating with frequencies that would eventually echo down through billions of years to reach us here, tonight, in the gentle darkness of your evening. These pressure waves were caused by the eternal dance between two fundamental forces. Gravity, ever the collector, was trying to pull matter together into denser clumps. But radiation pressure, the outward push of light and energy, was fighting back, trying to smooth everything out. This cosmic tug-of-war created oscillations, compressions, and rarefactions that rippled through the fabric of space itself. Imagine, if you will, the universe as a tremendous organ pipe, but instead of air flowing through brass tubes, it was filled with a glowing plasma of hydrogen and helium. As gravity squeezed regions of this plasma denser, they heated up and glowed brighter. The increased radiation pressure then pushed back, causing these regions to expand and cool. This created waves, vast acoustic oscillations that propagated through the entire observable universe. The scale of this cosmic symphony is almost impossible to comprehend. The wavelengths of these primordial sound waves stretched across millions of light years. The deepest notes had periods of millions of years. If you could somehow have floated in that ancient universe with impossibly sensitive ears, you might have heard a deep, resonant hum, like standing inside a cathedral-sized bell that was being struck once every few million years. But here's where the story becomes truly magical. About 380,000 years after the Big Bang, something remarkable happened. The universe had been expanding and cooling all this time, and finally, it became cool enough for electrons and protons to combine into neutral hydrogen atoms. This moment, which scientists poetically call recombination, changed everything. Suddenly, the universe became transparent. Light could travel freely for the first time, no longer constantly scattered by free electrons. This moment created what we now call the cosmic microwave background, a faint glow that still permeates the entire universe today. But more importantly for our story, it also froze the sound waves in place. When the universe became transparent, the cosmic symphony stopped. The acoustic oscillations that had been propagating through the plasma could no longer continue. The medium that carried them, that dense soup of charged particles, had suddenly become neutral and much less dense. It was as if someone had suddenly turned off the power to a vast cosmic orchestra, leaving only the echo of the last note hanging in the air. But those sound waves didn't simply disappear. They left their fingerprints on the very structure of the universe. Regions that had been compressed by the acoustic waves had slightly higher density, while regions that had been expanded had slightly lower density. These tiny variations in density, less than 1 part in 100,000, became the seeds from which all the large-scale structure of the universe would eventually grow. The cosmic microwave background radiation that we can observe today carries within it the fossilized imprint of these ancient sound waves. When we map the temperature variations across the sky, we're essentially looking at a snapshot of those primordial acoustic oscillations, frozen in time at the moment the universe became transparent. It's rather like looking at the surface of a pond just after the last ripple has passed. The water is still now, but you can see the pattern of where the waves once were, written in the distribution of floating leaves and debris. The cosmic microwave background is our cosmic pond, and the tiny temperature variations are the leaves that show us where the universe's first sound waves once traveled. Scientists have spent decades studying this ancient light, mapping it with ever greater precision using satellites and ground-based telescopes. What they've found is extraordinary. The pattern of temperature variations matches exactly what we would expect from acoustic oscillations in the early universe. We can see the harmonic structure, the fundamental frequency, and its overtones, just as a musician might analyze the complex sound of a violin by breaking it down into its component frequencies. The universe's first song was written in a major key, you might say. The fundamental frequency and its harmonics created a pattern that we can still read today, nearly 14 billion years later. These acoustic peaks in the cosmic microwave background tell us not just that the universe once rang like a bell, but they also reveal the universe's composition, its age, and its ultimate fate. But the story doesn't end there. Those ancient density variations, carved by the universe's first sound, became the scaffolding upon which everything we see today was built. The slight overdensities grew over millions of years, pulled together by gravity to form the first stars and galaxies. The slight underdensities became the vast cosmic voids that separate the great walls and filaments of galaxies we observe today. In a very real sense, the distribution of galaxies across the cosmos is an echo of that primordial music. When we look at the large-scale structure of the universe, at the way galaxies cluster and form vast cosmic webs, We're seeing the lasting influence of sound waves that traveled through space when the universe was less than 500,000 years old. Every star that lights the night sky, every planet that orbits those stars, every grain of cosmic dust that will one day become part of a new world. All of it traces its ultimate origin back to those first acoustic oscillations. The universe's song didn't just fade away. It became the very foundation upon which all of cosmic evolution was built. And here's perhaps the most beautiful part of all this cosmic music. We haven't just inferred the existence of these ancient sound waves from theoretical models and observations. We've actually converted them back into sound that we can hear with our own ears. By taking the data from the cosmic microwave background and scaling it to frequencies that human ears can detect, scientists have essentially played back the universe's first song. It's a haunting, ethereal sound, like wind rushing through cosmic caverns, or the deep breathing of the universe itself as it expanded and cooled in those first few 100,000 years. When you listen to these recreated sounds, you're hearing something that's both ancient beyond measure and intimately connected to your own existence. Those pressure waves, those acoustic oscillations, helped shape the very regions of space where our Milky Way galaxy would eventually form. The matter that makes up your body, forged in the hearts of stars billions of years later, was once part of that singing plasma, vibrating to the universe's first melody. There's something profoundly moving about this connection between sound and cosmic structure. Music, after all, is pattern in time, and the universe has been creating patterns since its very first moment. The same physical principles that allow a violin string to create beautiful music also governed the acoustic waves that rippled through the early universe. We are, in a very literal sense, children of that cosmic song. Every atom in your body once danced to those primordial rhythms, once vibrated in harmony with the universe's first symphony. The calcium in your bones, the iron in your blood, the oxygen you breathe, all of it can trace its ultimate ancestry back to those regions of space that were shaped by the universe's earliest acoustic oscillations. As you drift towards sleep tonight, perhaps you can imagine yourself floating in that ancient cosmos, surrounded by the gentle hum of creation itself. The universe was singing then, in frequencies too deep and vast for any earthly ear to hear, but singing nonetheless. And in a way, it's still singing now, in the whisper of wind through trees, in the rhythm of your heartbeat, in the quiet conversations between stars that have been going on for billions of years. The echoes of the Big Bang surround us always, a cosmic background radiation that bathes every corner of the universe in the afterglow of creation. But more than that, the patterns carved by the universe's first sound waves continue to influence the cosmos today. They're written in the distribution of galaxies, in the flow of dark matter through space, in the very structure of space-time itself. Tonight, as you close your eyes and let your mind wander among the stars, remember that you're listening to a story that began nearly 14 billion years ago with the universe's first song. That melody, those ancient acoustic waves, helped create the conditions that would eventually lead to planets and life and consciousness, and the quiet moment you're experiencing right now. The universe spoke its first word in the language of sound, and we're still learning to understand what it was trying to say. But we know this much. It was a song of becoming, a melody of possibility, the opening notes of a symphony that's still being written across the vast concert hall of space and time. Sweet dreams, fellow traveler. Now that the cosmos has cooled and atoms have formed, the universe stands at another crossroads. The afterglow of creation still bathes everything in soft microwave light. But something else is stirring in the darkness. Those tiny ripples we mentioned, the quantum fluctuations stretched across space during inflation, are about to become the architects of everything we see today. Picture the universe at this moment as a vast, dimly glowing cloud of hydrogen and helium gas. It's not perfectly smooth, mind you. There are subtle variations, places where the gas is just a fraction denser than elsewhere. These differences are almost imperceptible, like gentle hills and valleys in an otherwise flat landscape. But gravity, patient and persistent, has been taking notes. Where the gas is slightly denser, gravity pulls a bit harder. More atoms drift inward, making those regions denser still. It's a slow dance of accumulation, played out over millions of years. Think of it like cosmic snowball rolling down an endless hill, gathering more snow as it goes, growing larger and heavier with each turn. These growing clumps of matter aren't visible yet. There are no stars to light them up, no glowing nebulae to mark their presence. They exist as invisible scaffolding, dark matter and ordinary matter working together to build the framework upon which galaxies will eventually hang. It's the universe's first attempt at architecture, laid out in 3 dimensions across billions of light years. The structure that emerges is breathtaking in its complexity. Long filaments of matter stretch between dense nodes, creating what astronomers now call the cosmic web. Imagine a vast 3-dimensional spider web, but instead of catching flies, it's catching galaxies. The dense intersections where multiple filaments meet become the busiest neighborhoods in the cosmos, places where matter congregates and eventually lights up in brilliant displays of star formation. Between these filaments lie the voids, enormous empty regions where very little matter exists. These cosmic deserts can stretch for hundreds of millions of light years, containing perhaps a few lonely galaxies drifting through near-perfect emptiness. They're like the spaces between raindrops, vast and quiet, reminding us that even in a universe full of matter, emptiness still dominates. But it's in those dense filaments and their intersections where the real action begins. As matter continues to accumulate, the clumps grow more massive, their gravitational pull stronger. Eventually, they reach a critical threshold where the inward pull of gravity overcomes the outward pressure of the gas. When this happens, the gas begins to collapse in on itself, growing denser and hotter as it falls inward. Deep within these collapsing clouds, temperatures start to climb. Millions of degrees, tens of millions. The hydrogen atoms, pressed together under enormous pressure, begin to move faster and faster. Their nuclei, normally kept apart by electric repulsion, are forced closer and closer together. And then, in a moment that changes everything, fusion begins. Hydrogen nuclei smash together with such force that they stick, forming helium and releasing tremendous amounts of energy. That energy pushes outward as light and heat, creating a balance between the inward pull of gravity and the outward pressure of radiation. A star is born. This first generation of stars was unlike anything we see in the night sky today. They were massive, some weighing hundreds of times more than our sun. They burned incredibly hot and bright, but their lives were brief and violent. These population 3 stars, as astronomers call them, were made almost entirely of hydrogen and helium, the only elements available in the pristine early universe. Their nuclear furnaces worked overtime, fusing hydrogen into helium, helium into carbon, carbon into oxygen, and so on up the periodic table. For the first time since the Big Bang, the universe was creating new elements, forging them in the hearts of these stellar giants. It was cosmic alchemy on a grand scale, turning the simplest building blocks into the complex ingredients needed for planets, life, and everything we hold dear. But these stellar titans couldn't last forever. Their enormous mass meant they burned through their nuclear fuel quickly, sometimes in just a few million years. When the fuel ran out, gravity won decisively. The star's core collapsed catastrophically, then rebounded in an explosion so violent it could outshine an entire galaxy. A supernova. These explosions scattered the newly forged elements across space, seeding the surrounding gas clouds with carbon, oxygen, silicon, iron, and dozens of other elements. For the first time, the universe had ingredients more complex than hydrogen and helium. The stage was set for a new generation of stars, ones that could form planets, atmospheres, and eventually harbor the chemical complexity needed for life. The death of these first stars also left behind exotic remnants. Some collapsed into neutron stars, objects so dense that a teaspoon of their material would weigh as much as a mountain. Others became black holes, regions of space where gravity is so strong that not even light can escape. These black holes, particularly the more massive ones, would play crucial roles in the formation and evolution of galaxies. As this first generation of stars lived and died, they began to cluster together, drawn by their mutual gravitational attraction. Small groups formed first, then larger collections, as the invisible framework of dark matter continued to guide their assembly. These weren't yet the grand spiral galaxies we see today, but rather small, irregular collections of stars, the cosmic equivalent of villages before cities. The process was messy and chaotic. Star clusters collided and merged. Gas clouds crashed into each other, triggering new waves of star formation. Some early galaxies grew quickly by cannibalizing their smaller neighbors, while others remained stunted, never quite managing to gather enough material to become giants. Throughout this tumultuous period, the universe was transforming from a dark, quiet place into something more familiar. The first stars were beginning to ionize the hydrogen around them, their ultraviolet light stripping electrons from atoms and making the universe transparent again. This epoch of reionization marked the end of the cosmic dark ages. The universe was no longer dark. It was beginning to glow with the light of countless newborn stars. And yet, we're still just at the beginning of the story. These early star clusters and proto-galaxies were crude compared to the elegant structures we see today. The Milky Way, with its graceful spiral arms and organized stellar populations, was still billions of years in the future. But the foundation was being laid, one star at a time, one merger at a time, one generation of stellar death and rebirth at a time. The cosmic web was taking shape. Dark matter was shepherding ordinary matter into ever more complex structures, and the first black holes were growing at the centers of the densest regions. The universe had learned how to make stars, and now it was learning how to organize them into something grander. As we drift deeper into our cosmic journey, we find ourselves standing at one of the most remarkable chapters in the universe's story. The first galaxies had begun to shine, their light piercing the ancient darkness. But they were still young, chaotic, and finding their form. What happened next would transform these scattered collections of stars into the magnificent structures we see today, including our own Milky Way home. Picture the universe roughly 2 billion years after the Big Bang. It was a bustling, dynamic place, far removed from the quiet, dark ages we explored earlier. Galaxies were everywhere, but they looked nothing like the elegant spirals and stately ellipticals in our modern night sky. These early galaxies were smaller more irregular, and incredibly active. They were cosmic teenagers, full of energy and drama, constantly growing and changing. The key to understanding this transformation lies in something we've touched on before: the cosmic web. Imagine the universe as a vast three-dimensional spider web, with dark matter forming the invisible threads. Along these threads, normal matter, hydrogen and helium gas, flowed like water through cosmic rivers. Where these threads intersected, at the nodes of the web, matter accumulated in dense concentrations. These intersections became the birthplaces of the largest, most massive galaxies. But galaxy formation wasn't a gentle, orderly process. It was messy, violent, and spectacular. Small galaxies merged with larger ones in cosmic collisions that lasted hundreds of millions of years. Gas clouds, enriched with heavy elements from previous generations of stars, crashed into each other at tremendous speeds. These collisions compressed the gas, triggering massive bursts of star formation. Some regions of these early galaxies were birthing stars at rates hundreds of times faster than what we see in the Milky Way today. During this cosmic adolescence, something else was happening in the centers of these growing galaxies. The supermassive black holes we discussed earlier were also growing, feeding on the abundant gas and matter around them. As they fed, they released enormous amounts of energy, creating jets of plasma that stretched for thousands of light years. These jets didn't just sit there looking impressive. They actively shaped their host galaxies, heating up gas clouds, blowing away star-forming material, and essentially putting the brakes on runaway star formation. This relationship between supermassive black holes and their host galaxies is one of the most fascinating discoveries in modern astronomy. The black holes weren't just passengers along for the ride, they were co-pilots, helping to regulate the growth and evolution of their galaxies. When a galaxy formed stars too quickly, the central black hole would step in, quite literally blowing away the raw materials needed for star formation. It's a cosmic feedback loop that prevented galaxies from burning through all their fuel too quickly. As billions of years passed, this cosmic dance between star formation, black hole growth, and galactic mergers began to settle into more familiar patterns. The wild, irregular galaxies of the early universe gradually organized themselves into the shapes we recognize today. Those with enough rotational motion and a steady supply of gas settled into elegant spiral patterns, their arms outlined by bright young stars and glowing nebulae. Others, particularly those that had experienced multiple major mergers, became elliptical galaxies, their stars distributed in smooth, rounded halos. The Milky Way itself is a product of this long evolutionary process. Our galaxy began as a small collection of gas clouds and proto-galactic clumps, gradually accumulating mass through mergers with smaller galaxies. The stellar halo that surrounds our galaxy today is filled with the remnants of these ancient mergers, streams of stars that once belonged to smaller galaxies, now completely absorbed into our own. Even now, the process continues. We can observe several small galaxies being torn apart and absorbed by the Milky Way's gravitational embrace. What's remarkable about this galactic evolution is how it connects to our own existence. The heavy elements that make up rocky planets like Earth, carbon, oxygen, silicon, iron were forged in the nuclear furnaces of massive stars and scattered into space through supernova explosions. But these elements needed time to accumulate, to be recycled through multiple generations of stars, and to become concentrated enough to form the building blocks of planets and life. The early universe, dominated by hydrogen and helium, simply couldn't support the formation of Earth-like worlds. It took billions of years of stellar nucleosynthesis, galactic evolution, and cosmic recycling to create the chemical complexity necessary for planets, atmospheres, oceans, and eventually, life itself. We are not just made of star stuff, we are made of galaxy stuff, the product of billions of years of cosmic evolution and galactic maturation. This process of galactic evolution also helps explain one of the most profound questions in astronomy: why the universe looks the way it does today. The grand spiral galaxies, the massive ellipticals, the intricate cosmic web of filaments and voids, all of these structures are the result of this long process of gravitational collapse, merger, and evolution. What began as tiny quantum fluctuations in the early universe has grown, over billions of years, into the rich tapestry of cosmic architecture we observe today. As we continue our journey through the cosmos, drifting quietly through the history of galactic evolution, we begin to see how everything connects. The first stars seeded the universe with heavy elements. The first galaxies provided the gravitational wells where these elements could accumulate. The supermassive black holes regulated the growth of these galaxies, preventing them from consuming all their fuel too quickly. And through countless mergers, collisions, and interactions, the chaotic early universe gradually organized itself into the structured, beautiful cosmos we call home. The story of galactic evolution is still being written. Galaxies continue to merge, stars continue to form and die, and the cosmic web continues to evolve. Our own Milky Way will eventually merge with the Andromeda galaxy, creating a new, larger galaxy that astronomers have playfully named Milkomeda. Throughout the vast expanse of space, countless galaxies continue their ancient dance, spiraling, merging, and evolving in ways that echo the universe's earliest moments. We've traced the cosmic web from its primordial threads to the magnificent structures we observe today. But there's one more chapter in this grand story that deserves our attention: the role of sound itself in shaping everything we see. You might wonder how sound could exist in the vacuum of space, and you'd be right to question this. The universe today is largely silent, with no medium to carry sound waves between the stars. But in the beginning, when the cosmos was young and dense, things were very different. The early universe was filled with a hot, thick plasma, a sea of particles so tightly packed that sound waves could travel through it like ripples across a pond. These weren't just any sound waves. They were acoustic oscillations of cosmic proportions, created by the interplay between gravity trying to pull matter together and radiation pressure pushing it apart. Imagine the universe as a vast musical instrument, with dark matter providing the strings and radiation providing the bow. The result was a symphony of compression and rarefaction, waves of density flowing through the primordial plasma at nearly half the speed of light. The frequencies of these cosmic sounds were determined by the physics of the early universe itself. The size of the observable universe at that time set the fundamental tone, while smaller structures contributed higher harmonics. It was a deep, resonant chord that would have been felt as much as heard if anyone had been there to experience it. But this cosmic concert couldn't last forever. As the universe expanded and cooled, the plasma gradually thinned. Approximately 380,000 years after the Big Bang, something remarkable happened. The universe became transparent. Electrons and protons combined to form neutral hydrogen atoms, and suddenly light could travel freely through space. This moment, known as recombination, effectively ended the era of cosmic sound. When the music stopped, the sound waves didn't simply disappear. They were frozen in place, their patterns of compression and rarefaction preserved in the distribution of matter throughout the universe. The denser regions, where sound waves had compressed the plasma, became the seeds of future galaxies and galaxy clusters. The rarefied regions became the cosmic voids we observe today. This is why the cosmic microwave background radiation, that faint afterglow of the Big Bang, shows such intricate patterns. Those subtle temperature variations are the visual echoes of sound waves that traveled through the universe when it was only a few 100,000 years old. They're like the grooves on a cosmic record, preserving the memory of the universe's first and greatest symphony. Scientists have even found ways to convert these patterns back into sound. By analyzing the cosmic microwave background and translating its variations into audio frequencies, we can literally hear the echoes of the Big Bang. The result is a deep, droning hum punctuated by subtle variations, the actual sound of the universe being born. These primordial acoustic oscillations didn't just create pretty patterns in the sky. They were the architects of large-scale structure in the universe. The sound waves established a characteristic scale, about 500 million light-years, that we still see imprinted in the distribution of galaxies today. When astronomers map the positions of millions of galaxies, they find that they're not randomly scattered, but show a subtle preference for being separated by this acoustic scale. It's a bit like finding the echo of a bell ringing in the pattern of ripples on a lake long after the sound has faded. The waves are gone, but their influence lives on in the structure they created. Every galaxy cluster, every cosmic void, every filament of the cosmic web bears the imprint of those ancient sound waves. This acoustic signature has become one of our most powerful tools for understanding the universe. By measuring how the patterns in the cosmic microwave background relate to the distribution of galaxies today, cosmologists can determine fundamental properties of the universe: its age, its composition, the rate of its expansion. The cosmic sound waves have become a kind of standard ruler, allowing us to measure distances across the universe with unprecedented precision. But the story doesn't end there. While the universe as a whole fell silent after recombination, sound found new ways to make itself heard. Within the gas clouds that would eventually form galaxies, acoustic waves continued to play important roles. They helped regulate the formation of the first stars, influenced the growth of supermassive black holes, and shaped the evolution of galaxies themselves. Even today, astronomers detect sound waves propagating through the hot gas that fills galaxy clusters. These waves, generated by the activity of supermassive black holes, can be thousands of light-years long and take millions of years to complete a single oscillation. They're far too low in frequency for human ears to detect, but they're there nonetheless. A reminder that the universe hasn't completely forgotten how to sing. The relationship between sound and cosmic structure reveals something profound about the nature of the universe itself. The same physical processes that create the music we hear on Earth, the compression and rarefaction of matter, the propagation of waves through a medium, also shaped the largest structures in the cosmos. There's a deep connection between the song of a bird and the distribution of galaxies, between the vibration of a violin string and the cosmic web itself. This connection extends to the very atoms in our bodies. The elements heavier than hydrogen and helium were forged in the cores of massive stars, which themselves formed in regions of higher density created by those primordial sound waves. The calcium in our bones, the iron in our blood, the oxygen we breathe, all of it can trace its origins back to the cosmic symphony that played in the universe's infancy. So when you listen to music, remember that you're participating in something that began with the universe itself. the air molecules carrying sound to your ears, the atoms in your inner ear that detect those vibrations, even the neural patterns in your brain that interpret them as melody. All of these are part of an unbroken chain that stretches back to the first moments after the Big Bang. The early universe was not the cold, silent void we might imagine, but a place of cosmic music. And while that grand symphony has long since ended, its echoes continue to shape our world. Every time we look up at the night sky, we're seeing the frozen harmonies of creation itself, a visual music that tells the story of how something as beautiful and complex as our universe could emerge from the simplest of beginnings. In the end, the universe's first sound wasn't just noise. It was the fundamental creative force that gave birth to everything we see around us. From the largest galaxy clusters to the smallest particles, from the most distant quasars to the planet beneath our feet, everything bears the signature of that primordial song. Looking across the vast darkness of space, you realize that what appears to be silent emptiness is actually humming with the deepest music ever played. Tonight, we're listening to something extraordinary, the first sound the universe ever made, a cosmic symphony that began nearly 14 billion years ago and continues to shape everything around us, including you. But this wasn't sound as we normally think of it. There were no ears to hear, no air to carry vibrations, no instruments to play melodies. Instead, the universe's first song was written in the language of matter itself, composed of pressure waves that stretched across millions of light years, conducted by the invisible hand of gravity, and performed by a cosmic orchestra of hydrogen and helium atoms dancing to rhythms we're only now beginning to understand. To truly appreciate this ancient music, we need to travel back to when the universe was young, unimaginably hot, and filled with a plasma so dense that light itself couldn't escape. It was a time before stars, before galaxies, before planets, when the entire cosmos was smaller than a grapefruit, yet contained everything that would ever exist. The Big Bang wasn't an explosion in space. It was the birth of space itself, and with it came the universe's capacity to sing. In those first moments, the cosmos was a seething ocean of particles and energy, but it wasn't chaotic. Hidden within that apparent disorder were tiny fluctuations, quantum whispers that would grow into the largest structures we see today. These weren't random variations, but the seeds of something magnificent, density variations that would become the universe's first musical notes. As the universe expanded and cooled, these quantum fluctuations began to interact with the fundamental forces of nature. Gravity pulled matter together while radiation pressure pushed it apart, creating a cosmic tension that manifested as acoustic oscillations. Imagine the entire universe as a vast musical instrument, with regions of space contracting and expanding in rhythmic patterns, generating pressure waves that propagated through the primordial plasma like sound waves through water. These weren't gentle melodies, but thunderous oscillations of unimaginable scale. Each wave crest represented a region where matter was being compressed by gravity, while each trough marked an area where radiation pressure was winning the battle, pushing matter apart. The wavelengths of these cosmic sound waves stretched across millions of light years, creating patterns that would eventually determine where galaxies would form and where vast empty spaces would remain. The universe continued to expand and cool, but the acoustic oscillations persisted, growing stronger and more complex. Different regions oscillated at different frequencies, creating a rich harmonic structure that filled all of space. If you could have listened to the universe during this epoch, you would have heard a deep, resonant hum punctuated by the rhythmic beating of cosmic drums, each beat representing the compression and expansion of matter on scales that dwarf our solar system. This cosmic concert continued for hundreds of thousands of years, with the universe gradually growing larger and cooler. The plasma that filled space began to thin, and the temperature dropped from billions of degrees to merely thousands. As this cooling progressed, something remarkable was about to happen that would preserve the universe's first song for all eternity. About 380,000 years after the Big Bang, the universe reached a critical temperature of roughly 3,000 degrees Celsius. At this point, the cosmic plasma finally cooled enough for electrons to combine with atomic nuclei, forming the first neutral atoms. This moment, called recombination, was like someone suddenly turning off a cosmic fog machine. The universe, which had been opaque to light, suddenly became transparent. But recombination did more than just clear the cosmic fog. It also froze the acoustic oscillations in place, like a cosmic photograph capturing the universe's song at the exact moment the music stopped. The pressure waves that had been propagating through the plasma suddenly had no medium to travel through. The neutral atoms that formed didn't interact strongly with radiation, so the oscillations ceased, leaving behind a permanent record of where matter was compressed and where it was rarefied. This frozen pattern of density fluctuations became the cosmic microwave background, the afterglow of the Big Bang that we can still detect today. When we look at maps of this ancient light, we're seeing the visual representation of the universe's first sound, the peaks and valleys of those primordial acoustic waves preserved in the temperature variations of the cosmic microwave background. The patterns we observe are not random, but carry the signature of those ancient oscillations. Regions that were compressed by the acoustic waves appear as slightly warmer spots in the cosmic microwave background, while regions that were rarefied appear as cooler areas. The angular size of these temperature variations tells us about the wavelengths of the original sound waves, providing a direct measurement of the universe's acoustic properties when it was less than 400,000 years old. Scientists have carefully analyzed these patterns and discovered something extraordinary. The cosmic microwave background shows clear evidence of acoustic peaks, specific angular scales where the temperature variations are strongest. These peaks correspond to the fundamental frequency and harmonics of the universe's primordial sound, like analyzing the overtones of a cosmic bell that rang nearly 14 billion years ago. The first acoustic peak represents the fundamental frequency of the universe's sound, corresponding to oscillations that had just reached maximum compression when recombination occurred. The second peak corresponds to oscillations that had completed one full cycle and were again at maximum compression, while the third peak represents oscillations that had completed 1.5 cycles. Each peak tells us something different about the conditions in the early universe and the nature of the forces that shaped it. By studying these acoustic signatures, cosmologists have been able to determine fundamental properties of our universe with remarkable precision. The relative heights of the peaks tell us about the amounts of ordinary matter, and dark energy. The positions of the peaks reveal the geometry of space itself. The detailed structure of the acoustic oscillations has become one of our most powerful tools for understanding cosmic evolution. But the universe's first song didn't end with recombination. Those frozen density fluctuations became the seeds for all the structure we see in the cosmos today. Regions that were slightly denser than average, marked by the peaks of the ancient acoustic waves, began to collapse under their own gravity. Over millions of years, these overdense regions grew, eventually forming the first stars, galaxies, and galaxy clusters. The cosmic web that connects galaxies across billions of light years still bears the imprint of those primordial sound waves. The filamentary structure of the universe, with its vast empty voids separated by chains of galaxies, follows patterns that were established by the acoustic oscillations in the first few 100,000 years after the Big Bang. Every galaxy, every star, every planet exists where it does because of where those ancient pressure waves created regions of enhanced density. In a very real sense, the matter that makes up your body was influenced by these cosmic sound waves. The calcium in your bones, the iron in your blood, the oxygen you breathe, were all forged in stars that formed in regions shaped by the universe's primordial acoustics. The very atoms that allow you to think and dream carry within them the memory of that ancient cosmic music. Scientists have even been able to translate the patterns in the cosmic microwave background into actual sound waves that we can hear. By taking the temperature variations and converting them into audio frequencies, researchers have created recordings of what the universe might have sounded like during those first few 100,000 years. The result is a deep, haunting drone punctuated by subtle variations, like the universe's own cosmic chord progression. These audio reconstructions reveal that the early universe was remarkably musical. The acoustic oscillations followed harmonic patterns similar to those we find in terrestrial music, with fundamental frequencies and overtones that create a rich, complex sound. The universe, it seems, was born with an innate sense of rhythm and harmony that continues to influence cosmic evolution today. The discovery of the universe's first sound has profound implications for our understanding of cosmic origins. It provides direct evidence that the Big Bang was not a chaotic explosion, but a highly organized event that created structure and pattern from the very beginning. The acoustic oscillations show us that the universe has always been a place where order emerges from apparent chaos, where simple physical laws give rise to complex and beautiful phenomena. Moreover, the cosmic microwave background and its acoustic signatures offer a unique window into physics at energy scales far beyond anything we can achieve in terrestrial laboratories. The conditions in the early universe were so extreme that they tested the fundamental laws of nature in ways that would be impossible to replicate on Earth. By studying the universe's first sound, we're conducting experiments in fundamental physics using the entire cosmos as our laboratory. The story of the universe's first sound also reminds us of the deep connections between seemingly disparate phenomena. The same physical principles that govern the propagation of sound waves in air also shaped the evolution of the entire cosmos. The mathematics of acoustics, developed to understand musical instruments and architectural design, turns out to be essential for comprehending the origin of galaxies and the structure of space itself. As we continue to study the cosmic microwave background with ever more sophisticated instruments, we're discovering new layers of complexity in the universe's primordial song. Subtle polarization patterns in the ancient light may reveal gravitational waves from the earliest moments of cosmic inflation. Minute temperature variations could provide clues about the nature of dark matter and dark energy. Each new observation adds another note to our understanding of the cosmic symphony. The universe's first sound continues to influence cosmic evolution today. Dark matter, which doesn't interact with light, but does respond to gravity, still bears the acoustic signatures from the early universe. Computer simulations of cosmic structure formation show that the distribution of dark matter on large scales follows patterns established by those primordial oscillations, creating a hidden acoustic landscape that guides the formation of visible structures. Even more remarkably, the universe's expansion history is encoded in its acoustic properties. The sound waves that propagated through the early cosmos provide a standard ruler for measuring cosmic distances and a standard clock for measuring cosmic time. By comparing the acoustic signatures at different epochs, cosmologists can trace the evolution of the universe's expansion rate and test theories about dark energy and cosmic acceleration. The study of cosmic acoustics has also revealed unexpected connections between the very large and the very small. The quantum fluctuations that seeded the universe's first sound may have originated during a period of cosmic inflation, when the universe expanded faster than the speed of light. These microscopic quantum variations were stretched to cosmic scales, creating the acoustic oscillations that we observe in the cosmic microwave background. This connection between quantum mechanics and cosmology suggests that the universe's first song may contain information about the deepest levels of physical reality. The patterns we observe in the cosmic microwave background could provide clues about the quantum nature of space and time, the existence of extra dimensions, or the possibility of parallel universes. So here we are, standing at the threshold between ancient echoes and cosmic revelation. We've journeyed through the birth pangs of the universe, felt the ripples of primordial sound waves, and discovered how quantum fluctuations became the seeds of everything we see today. But now, in this gentle moment between sleeping and waking, let's explore how these cosmic harmonies still whisper to us across the vast expanse of time and space. The acoustic oscillations we've been following didn't simply vanish when the cosmic microwave background was released. They left their fingerprints everywhere, like a cosmic signature written in the language of matter and energy. These ancient sound waves, frozen in time at the moment of recombination, became the blueprint for all the large-scale structure we observe in the universe today. Think of it this way. Those pressure waves that once bounced through the primordial plasma created regions of slightly higher and lower density. When the universe became transparent and the waves stopped propagating, these density variations were preserved like fossils in the cosmic web. The slightly denser regions, enriched by the compression of sound waves, became the seeds around which the first stars and galaxies would eventually form. This connection between sound and structure is breathtakingly beautiful. Every galaxy cluster, every cosmic void, every filament of dark matter stretching across hundreds of millions of light years can trace its origins back to those first acoustic oscillations. The universe, in essence, is still singing the song it learned in its earliest moments, though now the melody is written in stars and space rather than pressure and plasma. Modern astronomers have found elegant ways to detect these ancient patterns. By mapping the distribution of galaxies across vast surveys of the sky, they can measure what's called the Baryon Acoustic Oscillation Scale. This is essentially the fossilized imprint of those primordial sound waves, preserved in the clustering of matter. It's like finding the echo of thunder long after the storm has passed, written not in sound, but in the very architecture of the cosmos. The scale is remarkably consistent, about 500 million light-years across, representing the distance sound could travel in the primordial plasma before recombination froze the waves in place. This cosmic standard ruler has become one of our most powerful tools for understanding the universe's expansion history and the nature of dark energy. It's extraordinary that something as ephemeral as sound, waves from the universe's infancy, can still guide our understanding of cosmic evolution today. But the influence of these ancient harmonics extends even deeper. The same processes that created the acoustic oscillations also determined the fundamental parameters of our universe. The interplay between matter, radiation, and the expansion of space set the stage for everything that followed. Without the precise balance of forces that allowed sound waves to propagate through the early universe, the cosmic microwave background would look entirely different, and the seeds for galaxy formation might never have been planted. Recent observations have revealed even more subtle connections between these primordial sounds and the universe we inhabit. The polarization patterns in the cosmic microwave background, caused by the last scattering of photons during recombination, carry information about the acoustic oscillation's final moments. These swirling patterns in ancient light tell us about the motion of plasma at the moment. The universe became transparent, like reading the sheet music of a cosmic symphony that played for only a brief, crucial moment in time. Scientists have also discovered that the acoustic oscillations influence not just where galaxies formed, but how they formed. The compression and rarefaction of matter by sound waves affected the initial mass distribution, influencing whether regions would collapse into massive galaxy clusters or remain as cosmic voids. In this sense, the first sounds of the universe helped determine the very neighborhoods where stars and planets would eventually emerge. The study of these cosmic acoustics has also opened windows into physics beyond our current understanding. Variations in the acoustic oscillation patterns could reveal the presence of additional types of particles or forces that were active in the early universe. Some theories suggest that primordial gravitational waves, ripples in space-time itself from the epoch of inflation, might have left subtle imprints on the acoustic oscillation patterns, providing a potential pathway to understanding the universe's very first moments. As we continue to build more sensitive instruments and conduct larger surveys of the cosmic web, we're essentially becoming better listeners to the universe's ancient music. Each new telescope, each improved measurement of galaxy clustering, each more precise analysis of the cosmic microwave background brings us closer to hearing the full symphony that played during the universe's youth. The profound beauty of this story lies in its universality. Those same acoustic waves that shaped the largest structures in the universe also influenced the formation of our own cosmic neighborhood. The Milky Way galaxy, our solar system, the Earth beneath your feet, and even the atoms in your body all owe their existence, in part, to sound waves that traveled through a universe smaller than our solar system today. And perhaps most remarkably, we've learned to reverse the process. Just as the early universe created sound from the interplay of matter and energy, we've learned to create sound from the patterns left behind by those ancient oscillations. The haunting tones we played earlier in our journey represent a kind of cosmic archaeology, translating the fossilized remains of primordial sound back into audible frequencies that our ears can perceive. This brings us full circle to a profound realization. The universe is not just expanding and evolving, it's resonating. From the quantum fluctuations that seeded inflation to the acoustic oscillations that shaped the cosmic web, from the formation of the first stars to the ongoing dance of galaxies across cosmic time, everything is connected by invisible threads of cause and effect, harmony and resonance. As you drift towards sleep tonight, carried by these gentle currents of cosmic understanding, remember that you are part of this grand symphony. The calcium in your bones was forged in the hearts of ancient stars. The iron in your blood was scattered by supernovae, and the very patterns of matter that allowed your existence were shaped by sound waves from the universe's dawn. The ancient reverberations that we've been following through cosmic time are still with us today, woven into the very fabric of how matter organizes itself across the universe. These primordial sound waves, frozen into the cosmic microwave background billions of years ago, continue to influence the formation and evolution of everything we see in the night sky. Consider the cosmic web, that vast scaffolding of dark matter and ordinary matter that stretches across billions of light years. The filaments and nodes of this structure, where galaxies cluster and form, are direct descendants of those original acoustic oscillations. The regions where sound waves compressed matter most efficiently became the dense hubs where galaxy formation accelerated. The regions where waves created rarefactions became the vast cosmic voids, those eerily empty spaces between the bright threads of the cosmic web. But the influence goes deeper than just large-scale structure. Within individual galaxies, the same principles that governed those early acoustic waves continue to shape star formation. Dense molecular clouds collapse under their own gravity, creating pressure waves that can trigger the birth of new stars. Supernovae explosions send shock waves rippling through the interstellar medium, compressing gas clouds and sparking fresh stellar nurseries. Even the spiral arms of galaxies like our own Milky Way are density waves, patterns of compression and rarefaction that sweep through the galactic disk, lighting up regions of star formation as they pass. The heavy elements that make up planets, and ultimately life itself, were forged in the nuclear furnaces of massive stars. When these stars died in spectacular supernovae, they scattered their enriched contents across space in expanding shells of hot gas. These stellar explosions created their own acoustic waves, mixing and distributing the carbon, oxygen, silicon, iron, and countless other elements that would eventually find their way into new generations of stars and planetary systems. Our own solar system formed from such enriched material, a swirling disk of gas and dust that condensed around the young sun some 4.5 billion years ago. The very atoms in your body, the calcium in your bones, the iron in your blood, the oxygen you breathe, all were forged in stellar cores and distributed by the acoustic shock waves of dying stars. In a very real sense, we are made of sound, the descendants of those first cosmic reverberations that began in the earliest moments after the Big Bang. Modern observations continue to reveal new layers of this cosmic symphony. Gravitational wave detectors like LIGO and Virgo have opened our ears to an entirely new kind of cosmic sound. The ripples in space-time itself created by colliding black holes and neutron stars. These gravitational waves carry information about some of the most extreme events in the universe, and they propagate through space at the speed of light, adding their own harmonies to the cosmic composition. Even more remarkably, scientists have discovered that black holes themselves can ring like bells when disturbed. Just as a struck tuning fork vibrates at specific frequencies, a black hole that has been perturbed by infalling matter or a collision with another black hole will oscillate in characteristic patterns. These oscillations, called quasi-normal modes, are encoded in the gravitational waves that ripple outward, allowing us to study the properties of these mysterious objects through their unique acoustic signatures. The study of stellar seismology has revealed that stars themselves are resonant cavities filled with acoustic waves that bounce back and forth within their interiors. By analyzing the subtle variations in a star's brightness caused by these internal oscillations, astronomers can peer inside stars and map their internal structure, much like geologists use seismic waves to study Earth's interior. Our own sun rings with thousands of different acoustic modes, creating a complex symphony of vibrations that we can detect and analyze to understand solar physics. Perhaps most intriguingly, some theoretical physicists have proposed that the universe itself might still be ringing with the echoes of its birth. These hypothetical primordial gravitational waves would be the direct descendants of quantum fluctuations in the fabric of space-time during the inflationary epoch, stretched to cosmic scales and still propagating through the universe today. If detected, they would provide a direct window into the first moments of cosmic history, allowing us to hear the universe's birth cry. The The connection between sound and cosmic structure extends to the very nature of time and space. Einstein's equations show us that matter and energy curve space-time, creating the gravitational fields that guide the motion of planets, stars, and galaxies. But these same equations also tell us that disturbances in this curved space-time propagate as waves, carrying energy and information across the cosmos. In a sense, the universe is a vast musical instrument, with matter and energy as the strings, and space-time itself as the resonating chamber. As we look to the future, new generations of telescopes and detectors will allow us to listen even more carefully to the cosmic symphony. The James Webb Space Telescope is already revealing the earliest galaxies, showing us how the first structures formed in the afterglow of those primordial sound waves. Upcoming gravitational wave observatories will be sensitive enough to detect the cosmic background of gravitational waves from the early universe, potentially allowing us to hear the echo of inflation itself. And perhaps most remarkably, we are beginning to understand that consciousness itself might be part of this cosmic symphony. The complex patterns of neural activity in our brains, the electrochemical signals that give rise to thoughts and emotions and dreams, all emerge from the same fundamental physics that governs the oscillations of stars and the ripples of space-time. We are not just observers of the cosmic symphony. We are participants in it, conscious arrangements of matter and energy that have learned to listen to their own origins. So as you drift towards sleep tonight, remember that you are surrounded by music, the gentle harmonies of a universe that has been singing since its first moment. The cosmic microwave background still whispers its ancient song. The stars continue their stellar seismology. Gravitational waves ripple through space-time. And somewhere in the quantum foam of reality itself, new melodies are being born. As we drift deeper into the universe's ancient song, it's time to explore one of the most profound ways this cosmic music has shaped our reality. The primordial sound waves we've been following didn't just create beautiful patterns in the cosmic microwave background. They became the sculptors of everything we see around us today, the architects of the grand cosmic web that connects every galaxy, every star, and ultimately, every atom in your body. Picture the universe as a vast musical instrument, with those early acoustic oscillations as the first notes played. But unlike a symphony that fades into silence, these cosmic melodies became frozen in time, preserved in the very structure of space itself. The peaks and troughs of those ancient pressure waves determined where matter would gather and where it would remain sparse, creating a three-dimensional map of density variations that would guide the formation of everything to come. The cosmic web, that magnificent scaffolding of the universe, is perhaps the most beautiful expression of this primordial music made manifest. Imagine a vast network of glowing filaments stretching across billions of light years, connecting massive galaxy clusters like luminous pearls on cosmic strings. These filaments aren't random. They follow the paths carved out by those first sound waves, creating highways of dark matter and gas along which galaxies formed and evolved. Between these filaments lie the cosmic voids, vast regions of space where few galaxies exist. These aren't empty spaces, but rather the quiet notes in the cosmic symphony, the places where the primordial waves created valleys of lower density. Some of these voids are so large that light takes hundreds of millions of years to cross them. They're like cosmic cathedrals of silence, punctuated only by the occasional lonely galaxy drifting through the darkness. The interplay between these dense filaments and sparse voids creates what astronomers call the cosmic web's foam-like structure. If you could shrink the observable universe down to the size of a kitchen sponge, the holes would be the voids, and the solid material would be the filaments where galaxies cluster. This isn't just a poetic metaphor. Computer simulations of the universe's evolution, guided by our understanding of those primordial sound waves, produce structures that look remarkably similar to actual observations of the cosmic web. But the influence of these ancient acoustic oscillations extends far beyond the largest scales. Within the filaments of the cosmic web, smaller structures formed through the same basic process. Dark matter halos, invisible gravitational wells that would later host galaxies, condensed at the intersections of cosmic filaments. The size and spacing of these halos were determined by the wavelengths of the primordial sound waves, creating a hierarchy of structure that cascades from the largest galaxy clusters down to individual galaxies like our own Milky Way. This hierarchical structure formation is one of the most elegant examples of how the universe's first sound continues to resonate through cosmic time. The same acoustic physics that created the largest structures also influenced the formation of smaller ones. Galaxy clusters, containing thousands of individual galaxies, formed where multiple filaments intersected. Galaxy groups, like our own local group containing the Milky Way and Andromeda, formed at smaller intersections. And individual galaxies formed within the dark matter halos that condensed along the filaments. The timing of this structure formation was also orchestrated by the primordial sound waves. The universe had to cool and expand enough for matter to begin clumping together, but not so much that the initial density fluctuations were washed out. This delicate balance, set by the acoustic physics of the early universe, determined when the first stars would ignite, when the first galaxies would form, and when the cosmic web would begin to take shape. As these structures grew, they began to influence each other through gravitational interactions, creating a complex dance of cosmic evolution. Galaxies would fall along the filaments toward larger clusters, sometimes colliding and merging along the way. Gas would flow along the filaments, feeding star formation in the galaxies and creating the intergalactic medium that fills the space between them. The cosmic web became not just a static structure, but a dynamic network through which matter and energy could flow. The influence of the primordial sound waves can even be seen in the internal structure of galaxies themselves. The rotation curves of spiral galaxies, the distribution of stars in elliptical galaxies, and the formation of supermassive black holes at galactic centers all bear the subtle imprint of those ancient acoustic oscillations. The universe's first sound didn't just create the cosmic web. It influenced every aspect of cosmic structure formation, from the largest scales down to the smallest. Modern astronomy has become remarkably skilled at reading these ancient acoustic signatures. By mapping the three-dimensional distribution of galaxies across the sky, astronomers can measure the characteristic scale set by the primordial sound waves, known as the Baryon Acoustic Oscillation Scale. This cosmic ruler, imprinted in the distribution of matter itself, provides one of our most precise tools for understanding the universe's expansion history and the nature of dark energy. But perhaps the most profound realization is that we ourselves are part of this cosmic web, connected to the universe's largest structures through the same primordial sound waves that created them. The atoms in your body were forged in stars that formed within galaxies that condensed from the cosmic web. The oxygen you breathe, the carbon in your cells, the iron in your blood, all trace their ultimate origin back to those first acoustic oscillations in the primordial plasma. This connection runs deeper than just our material composition. The very fact that planets like Earth could form in stable orbits around long-lived stars required the precise conditions set by the primordial sound waves. Too much initial structure, and the universe would have collapsed into black holes before stars could form. Too little, and matter would have remained too diffuse for gravity to create the dense environments necessary for stellar nucleosynthesis. The cosmic web continues to evolve today, driven by the same fundamental physics that shaped it billions of years ago. Galaxies continue to flow along the filaments, clusters continue to grow through mergers, and the voids continue to expand as the universe itself expands. But the basic pattern, the fundamental architecture, was set by those first sound waves when the universe was less than 1 million years old. As we look toward the future, this cosmic web faces an uncertain fate. The accelerating expansion of the universe, driven by dark energy, may eventually stretch the filaments beyond their ability to hold together. In the far future, billions of years from now, the cosmic web may dissolve as galaxies drift apart into an increasingly empty universe. But even then, the memory of those primordial sound waves will remain, preserved in the internal structure of galaxies and the distribution of matter within them. The universe's first sound didn't just create a single moment of cosmic music. It composed an eternal symphony, with movements that play out over billions of years and melodies that span the entire observable universe. Every galaxy cluster is a crescendo, every void a rest, every filament a flowing melodic line connecting the cosmic composition into a unified whole. And in the quiet moments, when you step outside on a clear night and look up at the stars, you're seeing the visible notes of this ancient song. The cosmic symphony reaches its crescendo in the very fabric of our modern universe. Those ancient sound waves, those primordial echoes from the first moments of creation, didn't simply fade away into cosmic silence. They evolved, they transformed, they became the invisible conductors orchestrating the grandest performance of all, the ongoing dance of galaxies, stars, and the intricate web of matter that surrounds us today. Think of it this way. If the early universe was a vast concert hall filled with acoustic waves, then today's cosmos is that same hall after the music has ended, but the reverberations continue to shape everything within it. The walls still vibrate with the memory of that first cosmic chord, and those vibrations continue to influence how new sounds, new structures, new stories unfold. The baryon acoustic oscillations we discussed earlier, those frozen sound waves locked into the cosmic microwave background, didn't disappear when the universe became transparent. Instead, they became a kind of cosmic ruler, a standard measure that continues to influence the distribution of matter on the largest scales. Even today, when astronomers map the positions of millions of galaxies across vast swaths of the universe, they can detect the subtle signature of those ancient acoustic peaks. Galaxies are still more likely to be found at specific distances from one another, distances that correspond exactly to the wavelengths of those primordial sound waves. It's as if the universe has been playing the same fundamental chord for nearly 14 billion years, and we're still hearing its harmonics in the arrangement of cosmic structure around us. The distance between galaxy clusters, the size of cosmic voids, the preferred scales at which matter clumps together, all of these carry the fingerprints of that first cosmic symphony. But the influence goes deeper still. Those sound waves didn't just shape where galaxies would form, they influenced how they would form. The acoustic oscillations created preferred scales for structure formation, and these scales cascaded down through cosmic history. The same physics that created the first acoustic peaks in the cosmic microwave background also influenced the formation of the first stars, the assembly of the first galaxies, and the growth of the cosmic web itself. Consider the process of galaxy formation. When the first dark matter halos began to collapse under their own gravity, they did so within the context of this acoustically structured universe. The same density fluctuations that had been shaped by sound waves in the early universe provided the seeds from which galaxies would grow. The cosmic web, that vast network of filaments and voids that gives large-scale structure its appearance, can trace its architecture back to those primordial acoustic oscillations. Even the formation of stars within galaxies carries echoes of that first cosmic sound. The turbulence in interstellar gas clouds, the compression waves that trigger star formation, the way stellar winds and supernova explosions propagate through the galaxy, all of these processes involve acoustic waves. In a sense, stars are still being born from sound, just as the first structures in the universe were shaped by the acoustic oscillations of the cosmic dawn. And what of the elements themselves? The carbon in your body, the oxygen you breathe, the iron in your blood, all of these were forged in the nuclear furnaces of stars. But those stars formed in galaxies that were positioned and structured by ancient sound waves. The very atoms that make up your physical being can trace their origins back through a chain of cosmic evolution that begins with acoustic oscillations in the primordial universe. This creates a remarkable connection between the most fundamental scales of cosmic structure and the most intimate details of our existence. The same acoustic physics that shaped the cosmic microwave background and positioned the first galaxies also influenced the chemical evolution of the universe. The elements that make life possible were created in stars that formed in galaxies whose positions were determined by sound waves from the first moments of cosmic time. The story becomes even more intricate when we consider the role of dark matter and dark energy in this ongoing acoustic symphony. Dark matter, which makes up the vast majority of all matter in the universe, doesn't interact electromagnetically, but it does respond to gravitational forces. The acoustic oscillations in the early universe were primarily driven by the interplay between ordinary matter and radiation. But dark matter provided the gravitational scaffolding upon which these oscillations could build lasting structure. Dark energy, meanwhile, has been stretching the fabric of space itself throughout cosmic history, gradually weakening the gravitational forces that hold cosmic structures together. This cosmic acceleration affects how acoustic features evolve over time, slowly erasing the smallest scale signatures while preserving the largest ones. In this sense, dark energy acts like a kind of cosmic damping mechanism, gradually quieting the reverberations of that first cosmic symphony. Yet even as dark energy stretches space and dilutes the influence of those ancient sound waves, new acoustic phenomena continue to emerge. Black holes, when they merge, create gravitational waves that ripple through space-time itself. These gravitational waves are, in a very real sense, the sound of black holes singing, and we've recently developed the technology to listen to this cosmic music directly. The detection of gravitational waves has opened an entirely new window into the acoustic nature of the universe. When two black holes spiral into each other and merge, they create a characteristic chirp in the fabric of space-time, a sound that can be detected by incredibly sensitive instruments like LIGO and Virgo. These gravitational wave detections are giving us a new way to listen to the universe, to hear the sounds of cosmic events that are invisible to traditional telescopes. Even more remarkably, scientists have discovered that stars themselves can act like cosmic musical instruments. The technique of astroseismology studies the acoustic oscillations within stars, the sound waves that propagate through stellar interiors and cause subtle variations in a star's brightness. By listening to these stellar songs, astronomers can probe the internal structure of stars, determine their ages, masses, and compositions, and even detect planets orbiting around them. Our own sun rings like a bell, with millions of different acoustic modes, causing its surface to rise and fall by tiny amounts. These solar oscillations, discovered through decades of careful observation, have revolutionized our understanding of stellar physics and provided a template for studying other stars throughout the galaxy. In this way, the acoustic theme that began with the cosmic microwave background has evolved into a rich symphony that continues to play out on every scale of cosmic structure. From the largest galaxy clusters to the interiors of individual stars, from the collision of black holes to the formation of planets, sound and vibration continue to shape the universe around us. The remarkable thing is that we, as conscious observers, have become part of this cosmic symphony ourselves. Our ability to detect the cosmic microwave background, to measure baryon acoustic oscillations, to listen to gravitational waves, and to study stellar oscillations means that the universe has evolved to the point where it can listen to itself. We are the universe's way of becoming aware of its own acoustic nature, of appreciating the ancient music that has been playing since the very beginning. This brings us to a profound realization. We are not separate from this cosmic symphony. We are part of it. Every heartbeat, every breath, every thought represents a continuation of the same physical processes that began with those first acoustic oscillations in the primordial universe. The sound waves that shaped the cosmic microwave background eventually led to the formation of galaxies, stars, planets, and ultimately to the emergence of life and consciousness. In this sense, listening to the universe's first sound is not just an act of scientific discovery, it's an act of cosmic self-recognition. When we detect the subtle temperature variations in the cosmic microwave background, we're not just studying ancient history, we're connecting with our own deepest origins. We stand at the threshold of silence, where the universe's first symphony played out in darkness. The cosmic microwave background that we've explored, that gentle afterglow of creation, carries within it something far more profound than just ancient light. It holds the memory of sound itself, the echoes of primordial acoustic waves that shaped everything we see today. In those earliest moments after the Big Bang, when the universe was a seething plasma of particles and radiation, sound waves rippled through this cosmic medium like thunderclaps in a primordial storm. These weren't sounds as we know them. There were no ears to hear, no air to carry them. But they were acoustic oscillations nonetheless. Pressure waves of compression and rarefaction that pulsed through the dense, hot plasma at nearly half the speed of light. Picture the early universe as a vast musical instrument, its strings made of matter and energy, its resonant chamber the fabric of space-time itself. Gravity pulled inward, trying to compress regions of slightly higher density. Radiation pressure pushed outward, resisting that compression. This cosmic tug-of-war created oscillations, waves of density that propagated through the plasma like sound waves through water. These primordial acoustic oscillations were governed by the same physics that creates music in our world today. Different wavelengths oscillated at different frequencies, creating what cosmologists call the acoustic peaks in the cosmic microwave background. Just as a violin string vibrates at specific harmonics, the early universe resonated with its own fundamental frequencies and overtones. But here's where the story becomes truly remarkable. When the universe was about 380,000 years old, it cooled enough for electrons and protons to combine into neutral hydrogen atoms. This moment, called recombination, suddenly made the universe transparent to light. But it also did something else. It froze the sound waves in place. Imagine a cosmic orchestra playing a complex symphony, and then suddenly, at the climax of a particularly intricate passage, time stops. The musicians freeze mid-note, their instruments suspended in perfect acoustic tension. That's what happened to the universe's first sound. The acoustic oscillations were caught mid-wave, their peaks and troughs preserved forever in the distribution of matter. These frozen sound waves became the seeds of everything that followed. Where the waves had compressed matter, gravity took hold more strongly, eventually forming the first stars and galaxies. Where the waves had rarefied the plasma, vast cosmic voids would stretch across billions of light years. The universe's first sound had become its architectural blueprint. Scientists have learned to listen to these ancient echoes by studying the cosmic microwave background with exquisite precision. The temperature variations we observe, differences of mere millionths of a degree, are the visual representation of those primordial sound waves. By analyzing their patterns, we can hear the universe's first chord, determine its fundamental frequency, and understand the cosmic composition that gave it voice. Remarkably, researchers have even translated these ancient acoustic signatures into audible sound. By speeding up the oscillations that once took hundreds of thousands of years to complete, they've created haunting melodies that represent the universe's birth song. It's a deep, resonant tone that rises and falls like a cosmic whale song, carrying within it the story of creation itself. But the universe's musical legacy didn't end with recombination. Those frozen sound waves continued to influence cosmic evolution, guiding the formation of the cosmic web. That vast network of filaments and voids that gives the universe its large-scale structure. Every galaxy cluster, every supercluster, every cosmic void carries the imprint of those original acoustic oscillations. Even today, we can observe the continuing echoes of the universe's first sound. Baryon acoustic oscillations, the stretched-out descendants of those primordial waves, still influence how galaxies cluster together. They've become a cosmic ruler, allowing astronomers to measure distances across the universe and trace the expansion history of space-time itself. The story doesn't end there. Modern gravitational wave detectors like LIGO and Virgo are beginning to detect new forms of cosmic sound. The ripples in space-time created when black holes collide or neutron stars merge. These gravitational waves travel at the speed of light, carrying the sounds of cataclysmic events across the cosmos. In a sense, we're learning to hear the universe sing in real time. Even stars themselves are musical instruments. The field of asteroseismology studies the acoustic oscillations within stellar interiors, using sound waves to peer into the hearts of distant suns. Just as a bell's tone reveals its composition and structure, a star's acoustic signature tells us about its age, mass, and internal processes. The universe's first sound connects us to the deepest mysteries of existence. Those primordial acoustic waves arose from quantum fluctuations in the very early universe. Tiny uncertainties in the position and energy of particles that were stretched to cosmic proportions by inflation. In a very real sense, the music of the cosmos began with quantum whispers that grew into the grand symphony we observe today. This cosmic acoustics also provides crucial evidence for our understanding of dark matter and dark energy. The precise patterns of the sound waves encoded in the cosmic microwave background tell us about the universe's composition, how much ordinary matter, and dark energy it contains. The universe's first sound has become one of our most powerful tools for understanding the nature of reality itself. As we drift towards sleep, listening to this tale of cosmic music, We might marvel at the profound connection between sound and structure, between vibration and form. The universe's first sound waves didn't just fade away, they built everything. They shaped the distribution of galaxies, influenced the formation of stars, and ultimately created the conditions that allowed planets to form and life to emerge. In your own body, atoms forged in stellar cores are arranged in patterns that can trace their lineage back to those primordial acoustic oscillations. The calcium in your bones, the iron in your blood, the oxygen you breathe, all were created in stars that formed because the universe's first sound waves compressed matter in just the right way, just the right places, at just the right time. So as you settle into rest, remember that you are not just made of star stuff, you are made of sound waves, cosmic music frozen into matter and given the gift of consciousness. As we draw near to the end of our cosmic journey, we find ourselves confronting one of the most profound questions in all of science. Are we alone? Throughout our exploration of the universe's first sounds, we've traced the echoes of the Big Bang as they rippled through space and time, eventually giving birth to the very structures that made life possible. But those ancient acoustic waves didn't just create galaxies and stars. They orchestrated something far more remarkable. They created the conditions for consciousness itself to emerge, to listen back to its own origins, and to wonder about its place in the vast symphony of existence. The baryon acoustic oscillations we've explored weren't merely cosmic construction workers, building the scaffolding of reality. They were composers, writing a score that would eventually be performed by every atom in your body, every thought in your mind, every word you speak. 8 billion years ago. Consider this remarkable chain of causation. Quantum fluctuations in the first fraction of a second after the Big Bang created tiny variations in density throughout the universe. These variations became acoustic waves, pressure oscillations that traveled through the hot, dense plasma of the early cosmos. When the universe cooled and these waves froze into the cosmic microwave background, they left behind a pattern, a cosmic fingerprint that influenced where galaxies would form, where stars would ignite, and ultimately, where planets capable of supporting life would emerge. But the story doesn't end there. Those same patterns that determined the large-scale structure of the universe also influenced the chemical evolution of the cosmos. The waves guided the formation of the first generation of massive stars, which forged the heavy elements essential for life: carbon, oxygen, nitrogen, iron. When these stellar giants exploded as supernovae, they scattered these elements across space, seeding future generations of stars and planets with the building blocks of complexity. The acoustic oscillations even influenced the formation of our own solar system. The density variations they created affected the distribution of matter in our galactic neighborhood, determining where molecular clouds would collapse to form new stars. The sun condensed from one such cloud, and the planets, including Earth, formed from the leftover material. In a very real sense, we are children of those ancient sound waves, sculpted by their influence across billions of years. As consciousness emerged on Earth, it carried within itself the memory of these cosmic origins. The same physical laws that governed the propagation of sound waves in the early universe govern the neural oscillations in your brain. The same mathematical harmonies that describe baryon acoustic oscillations also describe the rhythms of thought, the patterns of memory, the cadences of language. When you listen to the universe's story, you're not just an external observer. You're part of the story itself, a temporary arrangement of atoms that the universe has assembled to know itself. This brings us to perhaps the most stunning realization of all. Consciousness might not be a rare accident in the cosmos, but rather an inevitable consequence of the universe's acoustic architecture. The same waves that created the cosmic web of galaxies also created the complex structures necessary for information processing, pattern recognition, and self-awareness. If this is true, then consciousness, in some form, might be woven into the very fabric of reality, emerging wherever the conditions allow. The search for extraterrestrial intelligence takes on new meaning when viewed through this lens. We're not just looking for radio signals from distant civilizations. We're listening for other instruments in the cosmic orchestra, other arrangements of matter that have learned to hear the universe's ancient song. Every galaxy cluster, every stellar nursery, every planet in the habitable zone of its star represents a potential venue where consciousness might arise to appreciate the beauty of existence. Even if we never make contact with other intelligent beings, we're not truly alone. We're connected to every star in the sky through the acoustic waves that shaped their formation. We're linked to every galaxy we observe through the same primordial oscillations that influenced their growth. The cosmic microwave background radiation that bathes the entire universe carries within it the memory of our shared acoustic heritage. As you drift towards sleep tonight, remember that you're not separate from the cosmos. You're an integral part of its ongoing symphony. The atoms in your body were forged in stellar cores and scattered by supernovae whose formation was guided by ancient sound waves. The patterns of your thoughts echo the same mathematical relationships that govern the structure of galaxy clusters. Your heartbeat resonates with rhythms that began with the universe's first sound. The baryon acoustic oscillations that we've explored represent more than just an interesting chapter in cosmic history. They reveal the universe as a vast, interconnected system where the smallest quantum fluctuations can influence the largest structures, where sound waves from the dawn of time continue to shape reality today, and where consciousness emerges as the universe's way of listening to its own story. In this grand acoustic tapestry, we are not merely observers, but active participants. Every discovery we make, every pattern we recognize, every moment of wonder we experience adds new harmonies to the cosmic composition. The universe's first sound has become, through us, the universe's first listener. And in that listening, in that moment of recognition and awe, the ancient acoustic waves complete their ultimate purpose, not just to build galaxies and stars, but to create beings capable of appreciating the profound beauty of their own cosmic origins. And so, dear listener, we arrive at the final movement of our cosmic symphony. We've journeyed through the primordial darkness of the early universe, witnessed the birth of the first stars, and followed the graceful dance of galaxies as they formed and evolved across billions of years. We've explored how sound itself, those ancient acoustic waves from the Big Bang, shaped everything we see today, from the largest galactic clusters to the smallest details of our own existence. But perhaps the most remarkable discovery of all is that this cosmic music never truly ended. It simply transformed, evolved, and found new instruments to play upon. The gravitational waves that ripple through space-time today carry the same fundamental rhythms that once shaped the cosmic microwave background 8 billion years ago. Even now, as you rest in the quiet of your evening, the universe continues its ancient song. Dark matter streams through cosmic filaments like invisible strings being plucked by gravity's patient hand. Black holes merge in distant galaxies, sending tremors through the fabric of space itself. New stars ignite in stellar nurseries, adding their voices to the eternal chorus. The cosmic web grows and shifts, its vast architecture still guided by those primordial sound waves that taught matter how to gather, how to dance, how to become. And you are not merely listening to this cosmic symphony. You are part of it. Every atom in your body was forged in the nuclear furnaces of ancient stars, each one carrying the acoustic signature of its stellar birthplace. The calcium in your bones, the iron in your blood, the oxygen you breathe, all of it bears the imprint of cosmic sound waves, of stellar oscillations, of the universe learning to sing. Your DNA itself is a kind of music, a four-note symphony written in the language of life. Your heartbeat, your breathing, the electrical rhythms of your thoughts, these too are part of the great composition. Notes in a melody that began with the Big Bang and continues to play through you, in you, as you. The cosmic microwave background still hums around us, that gentle afterglow of creation carrying within it the fossilized sound of the universe's first voice. Radio telescopes strain to hear the whispers of hydrogen clouds in distant galaxies, their songs red-shifted by billions of years of cosmic expansion. We've learned to translate these frequencies into audible sound, to literally hear the music of the spheres, and in doing so, we've discovered that the universe has always been singing to us. Sometimes, in the deepest reaches of space, we detect something extraordinary, the gravitational wave signature of two black holes spiraling into each other, their final dance creating ripples in space-time that carry the acoustic fingerprint of their merger. These waves, predicted by Einstein but only recently detected, are the universe's way of continuing that first cosmic song in a new key, with new instruments, across new scales of space and time. Even our technology participates in this ancient symphony. The radio waves that carry our communications, the electromagnetic radiation from our devices, the gentle hum of electricity through our cities, all of this adds to the universe's acoustic tapestry. We are not separate from the cosmic song. We are composers within it, adding our own melodies to a composition that began before Earth existed and will continue long after our sun has cooled to a distant memory. The Milky Way itself rotates with a rhythm, its spiral arms sweeping through space in a grand celestial waltz that takes 225 million years to complete. Our solar system rides these galactic currents like a note sustained across geological time, while the planets in their orbits add their own harmonic frequencies to the local arrangement. Even the moon's tidal pull creates acoustic waves in Earth's oceans, connecting the rhythm of the tides to the broader cosmic symphony. As we've learned to listen more carefully to the universe, we've discovered that sound and vibration are fundamental to reality at every scale. Quantum fields fluctuate with their own frequencies. Atoms vibrate in their crystalline lattices. Molecules dance to thermal rhythms. Cells pulse with biochemical beats. Organs maintain their physiological harmonies. And consciousness itself, that mysterious emergence of awareness from matter, may be nothing more than the universe becoming capable of hearing its own song. The future promises even more magnificent music. As galaxies continue to merge and evolve, as new stars are born and old ones die, as the cosmic web grows ever more complex, the universe's symphony will develop new themes, new variations on its ancient melodies. The James Webb Space Telescope and future instruments will let us hear deeper into cosmic history, perhaps even detecting the gravitational wave echoes of cosmic inflation itself, the very moment when the universe first learned to sing. Someday, we may discover that consciousness is not unique to Earth, that other worlds have developed their own instruments for participating in the cosmic symphony. The songs of alien civilizations, the technological harmonies of advanced species, the collective music of a universe awakening to itself. These too may be part of the grand composition that began with those first acoustic oscillations in the primordial plasma. But even if we are alone, even if Earth is the only place where matter has learned to listen to its own cosmic heritage, that makes our existence no less miraculous. We are the universe's way of hearing itself, of appreciating its own ancient song, of marveling at the journey from those first sound waves to the complex harmonies of life, consciousness, and love. Tonight, as you drift toward sleep, remember that you are cradled in this cosmic symphony. The same fundamental forces that shaped the first galaxies are gently holding you now. The same acoustic principles that taught matter how to dance are present in your every breath, your every heartbeat, your every dream. You are not a separate observer of the universe's song. You are one of its most beautiful instruments, capable of adding your own unique voice to the eternal composition. The echoes from the Big Bang surround you still, fainter now but never silent, woven into the fabric of space-time itself. They whisper through the cosmic microwave background, pulse through gravitational waves, resonate in the oscillations of distant stars, and live on in the very atoms of your being. From the first sound to the last, from the birth of time to whatever lies beyond, the universe has been and always will be a symphony of unimaginable beauty and complexity. And you, dear listener, you are both audience and performer, observer and participant in this grandest of all concerts. Sleep now, and let the cosmic music carry you gently through the night, knowing that when you wake, the symphony will still be playing, and your voice will still be part of the song.